And what we really wanted to do was, I mean, we didn't even know, could you make a wavefront measurement from a laser? This was all speculation. So we wanted to propagate a laser toward a star, directly toward a star, so it was perfectly aligned, because there's another effect in the atmosphere that no matter what direction if you look in slightly different directions, you get a different wavefront distortion. This is really a mess. I mean, if you go 10 microradians off of a star, for instance, you get a completely different wavefront than if you go right at the star. Or the target, a satellite, for instance. So,
was this part of the Star Wars things?
It eventually became part of it. In 1983, when Star Wars came along, and they went around and swooped up everything, this got caught up in that. And for a while, we were funded by SDIO. But eventually they figured out that this, they didn't have that much use for it, and so it went over to the Air Force. But, so in the fall of 1982, we set up this experiment, and the idea, we had two objectives. One, could we make a wavefront measurement from the laser? And number two, if we simultaneously could make a measurement from the laser and the star, what was the difference? Fried predicted there would be a difference because, the laser was only going to be, in our case, it was only 5 kilometers high. We only had a 40 centimeter, back here on the bench, which you can't quite see, there's an off-axis parabola. So we had this 10 hertz pulse laser. So this was not a closed loop experiment. It was open loop. We had to make a measurement from the laser and a measurement from the star. And here's an example. We built a special piece of optics that used polarization. And, I had a couple of lieutenants. We had, the most rudimentary computers you could imagine. And so we had our 40 centimeter aperture was divided into 18 regions with these little, what we call Risley prisms, that we could rotate and tilt the wavefront so that we could make these spots, 18 spots on a camera. And we could look at Polaris and we could look at the laser. The first thing you notice is the laser spots are much bigger and uglier than the ones from Polaris, because it's not a point source. It's not, it's a finite size source in the sky. So it's harder to find the centers of these. So by finding the centers and how they deviate from their average position, because what happens is, as the turbulence changes, it moves these spots just a little bit. And this is the way we do it in real time. We have a CCD array, and we have an array of lenslets in front of it. We look at the spot positions from each lens, and we watch how it moves around. That tells us the local tilt, the distortion, what direction the light is traveling over that section of the aperture. We then have to put that information back together to create the wavefront, and how much we have to move the deformable mirror to correct it. So we did this, and we were able to reconstruct. Well, first of all, we were able to make wavefront measurements. So here's the wavefront that we measured, one example from the star, and here's what we got from the laser, and here's the difference. These are the square of the wavefronts. And so then we could, mask off part of the aperture and determine, as the aperture increased, how did the error change between these two wavefronts. And so we made a plot of that. And the dashed line here was Fried's theory. And even though we had a limited size data set because of the limited aperture we had, 40 centimeters, it agreed perfectly. So I show you two example data sets. And eventually, in 1991, we were able to publish this in the journal Nature. But this was a very important chart, because it basically said Fried's theory was right, and that we could make a wavefront measurement, and that if we wanted to correct a big aperture, we knew how high the beacon had to be. And so that kind of ignited the project, and the first thing I did was try to buy a telescope. And because we needed to be able to point this in the sky and track satellites and do all kinds of stuff. And so we ended up with a 1.5 meter telescope that we bought from what is now used to be Contravi's. It's now Berkshires, I guess, in Pittsburgh. And it's another interesting war story. I went in there. It turns out that NASA had a 40 centimeter telescope with this mount design that they had on a trailer that they used for laser ranging against satellites with retro reflectors. So I went to Contravi's and I sat down with him one morning. I said, I'm interested in a bigger version of this. Could you make it 50 centimeters? Yeah, oh yeah, we can do that. This is system engineering. I shouldn't be telling this to quality people. So then I said, can you make a 70 centimeter version? Yep, we can do that. Can you make it 1 meter? And so they huddled up a little bit, did some scratching around, and yep, we can do 1 meter. So then I said, how about, can you do 1.5 meters? And then they said, let's break for lunch. We did. They came back after lunch and they said, we can do 1.5 meters. And I said, I'm afraid to ask, can you do 1.8 meters? No, we can't do 1.8 meters. So they enlarged the fork, the mount, on that 40 centimeter telescope to 1.5 meters. They put a bigger motor in there, and so on and so forth. And so this became our 1.5 meter telescope. It cost $750,000. At the time, SDIO was in control of the budget. The people running SDIO were from mostly Lincoln Laboratory. So I thought, I've got a snowball's chance in hell of getting this funded because I was kind of competing with Lincoln Laboratory in this business. Lincoln Laboratory had been doing adaptive optics for laser weapons. And so I sent the proposal up, and there was gnashing of teeth and so forth, and they finally, I guess, called the Air Force, and the Air Force and SDIO split the cost. And in 1987, we got the telescope. And I don't have all the details of when it arrived, but it was an interesting set of circumstances. So in the meantime, Charles Towns, the Nobel laureate for inventing the laser, became interested in this project because he was briefed on it fairly early on. He was interested in atmospheric fluctuations in general because he was building an interferometer, and he had 2 large mirrors, and he wanted to interfere the beams, and he wanted to correct them. And so he came to the SOR on several occasions to follow the progress of the experiment. And he was instrumental in helping getting this information declassified in 1991. The thing that mostly helped that was the demise of the Soviet Union. We worked on it for about 2 years. I mean, I knew that this was going to be a great benefit for astronomy, and we really ought to get this into the hands of the astronomers. So in May of 1991, at the American Astronomical Society meeting in Seattle, I gave the first public released information on this technology using lasers to run adaptive optics. And this picture was made at a press conference the next day. And this is Dr. Towns here, and this is a fellow from Lincoln Laboratory, Charles Pemmerman, who eventually did get the sodium part of the experiment to work, but it took him an extra couple of years because of the problems with the laser. And after that, in the fall of that year, we published in Nature, and I don't know if any of you have published in Nature, but the editors are very, shall we say, stuffy. They're very British, they're very serious all the time. Mostly they reject your papers if you submit them. But they put in an editorial in this issue, and I had sent this picture along, and so they titled the editorial "Beam Me Up, Scotty." So it was really quite a